Just imagine you carrying a lot of weight on your back just to do simple calculation, or you needing a truckload of equipment just to make a phone call. Sounds absurd, doesn't it? Well, that's exactly how things would have been if transistor was not invented. But what exactly is a transistor? How did it revolutionize everything we know about technology today? Before diving into what transistor is, let's first understand how computers are designed to work. Computers are logical machines. At the core of every computer, no matter how advanced or simple, is a language that it understands. And that language is binary. Just two symbols, 1 and 0. You might think of these numbers as just simple digits. But no, they hold the key to how computers perform complex tasks, ranging from basic calculation to processing massive amounts of data, running intricate algorithms, and enabling advanced technologies like artificial intelligence and virtual reality. In binary, 1 represents an on state, while 0 represents an off state. These ones and zeros combine to form bits, the smallest unit of data. And when 8 bits are grouped together, they form bytes. For example, the number 5 in binary is represented using 3 bits, 1, 0 and 1. So that means there should be a mechanism which automatically switches on, off and on to represent the number 5. Similarly, for every action, every calculation, every image or a video you see on your computer works on the same principle of switching on and off, but more complicated. Just imagine this. If your computer broke down today, you would take it to a technician to repair it. But back in early days of computing, you might have needed to visit a mechanic instead. Why? Because the very first computers were mechanical machines, relying on gears, levers, and electromechanical relays to function. The introduction of electromechanical relays brought a significant improvement. These switches allowed machines to process binary data by physically opening and closing circuits. Relays automated calculations and logical operations, moving computers one step closer to modern machines. How exactly relays function? When an electrical current flows through the relay's coil, it creates magnetic field that moves a mechanical arm, either completing or breaking a circuit. It is this ability of relays which made its way to computing devices. However, they have their set of flaws. The major ones are performance and reliability. One of the most famous and humorous incidents in early computing history occurred with Harvard Mark II computer in 1947. During a routine check, engineers discovered that the machine had malfunctioned due to very unexpected culprit, an actual moth. The insect had found its way into one of the machine's relay and was trapped inside, causing an electrical fault. This seemingly trivial event turned out to be monumental in shaping computer jargon. The engineers carefully removed the moth, taping it into machine's logbook with the note, first actual case of bug being found. The term bug had been informally used in engineering to describe errors or glitches for decades. But this incident gave it a literal example. More importantly, it popularized the term debugging, which is still used today to describe the process of identifying and resolving issues in software and hardware industries. Just imagine a time when technology was dominated by using giant glass bulbs, and a single calculation could even fill an entire room with heat and noise. Well, I'm talking about something called as vacuum tubes. In the first half of 20th century, vacuum tubes, also called as valves, served as a cornerstone of electrical circuits. These glass cooling bulbs played a pivotal role in shaping the modern era of electronics, enabling significant advancement across various fields. Without vacuum tubes, the electronic world as we know it today, along with the modern convenience we take for granted, would not have taken off. These remarkable inventions laid the groundwork for digital age, paving the way for further advancements in electronics, computers, and communication technologies. For the first time in human history, after invention of vacuum tubes, machines could perform calculations electronically rather than mechanically. Vacuum tubes served as a primary component for processing and storing data, replacing older electromechanical relays, thereby drastically increasing computational speed. This innovation enabled early computers to tackle problems that were previously unimaginable for their time. However, the reliance on vacuum tubes came at a cost. The first and major drawback was size and complexity. The sheer number of vacuum tubes required for these early computers made them enormous and highly complex. These machines often filled an entire room. For instance, one of the first general-purpose computers utilized over 17,000 vacuum tubes, contributing to its colossal size and a weight of nearly 30,000 kilograms. The second and major drawback: vacuum tubes were power-hungry giants. They consumed vast amounts of electricity, often drawing as much power as small towns. Some installations even required dedicated power plants to meet their energy consumption. The third drawback: vacuum tubes were delicate components, highly prone to failure. On an average, a single tube could burn out every few hours, disrupting operations. This meant teams of engineers and technicians were on constant standby, replacing tubes and troubleshooting issues to keep the systems functional. The fragility of these machines posed a significant bottleneck for their reliability and efficiency. Fourth drawback: heat generation. Vacuum tubes consumed a lot of energy, and a significant portion of this energy was lost as heat. This caused the machines to generate immense amount of heat, which not only reduced their efficiency but also posed risk to the surrounding components. Despite these drawbacks, they were groundbreaking innovative computers built on this vacuum tubes technology. The most famous one at that time was the Colossus from 1943. This was the world's first programmable digital computer built by British engineers to decode German messages during World War II. It used little over 2,400 vacuum tubes. The another most famous computer was the ENIAC from 1945. It was built for US Army, and it housed an astonishing 17,400 vacuum tubes, consuming massive 150 kilowatts of power and weighing close to 30,000 kilograms, which is unbelievable. But then everything changed. The world was about to witness a technological revolution, the invention of transistor. The 1940s were a time of technological challenge and opportunity. At Bell Labs, the research arm of AT&T, engineers faced a growing problem. The world's demand for telephone lines and amplifiers was skyrocketing. The bulky, inefficient vacuum tube technology couldn't keep up. What the world needed was something smaller, faster, and more reliable. In 1947, at Bell Labs, three visionary scientists, John Bardeen, Walter Brattain, and William Shockley, unveiled a breakthrough: the transistor. Unlike vacuum tubes, the transistor was smaller, faster, far more efficient. The transistor's impact was so profound that in 1956, these three visionary scientists were awarded the Nobel Prize in Physics. Their invention didn't just improve electronics, it transformed the world. It laid the foundation for devices which we use today, from basic calculators to supercomputers. The invention of transistor marked the end of vacuum tube era and gave birth to new technological age. What started as a solution for amplifiers at Bell Labs would go on to power the future of computing, communication, and innovations. A transistor is a tiny semiconductor device designed to control the flow of electrical current. It can regulate current, amplify electrical signals, and even act as a switch or a gate. At the heart of every transistor is a material called semiconductor. Semiconductors are unique because they exist in a middle ground. Unlike conductors like copper, which freely allow electricity to flow, and insulators like plastic, which blocks electricity completely, semiconductor can conduct electricity under specific conditions, making them perfect for precise control in electronic circuits. One of the most common semiconductor used in transistors is silicon, a chemical element abundant in sand. However, Silicon on its own isn't naturally conductive. To make it suitable for transistor, it undergoes a process called doping. Doping is a process which makes silicon able to conduct electricity in a controlled way when needed. How does transistor work? Imagine transistor as a water pump system. Every transistor has three main components or terminals: emitter, base, and collector. The first terminal, emitter. This is like a water tank or source where the water starts its journey. It releases the water into the system. The second terminal, base. Think of this as a valve or a gate. By applying a small effort like turning the valve slightly, you can control whether the water to flow or not. The third terminal, collector. Finally, the collector is like a pipe leading the water to where it's needed, completing the flow. This trio works together to control the flow of electricity, making transistor indispensable in modern electronics. What makes transistor incredible is their speed of operation. Modern transistors are incredibly fast, switching on and off billions of times per second. This speed is the backbone of our modern digital world. Over the years, as transistors evolved, they didn't just become faster, they also became smaller and more efficient. Today's advanced processors packs billions of transistors onto a single chip, enabling compact devices with immense power. In 1965, Roden Moore, co-founder of Intel, made a groundbreaking observation. He noticed that the number of transistors on a chip was doubling roughly every 2 years, while the cost per transistor was decreasing. This observation, now known as Moore's law, became a guiding principle for semiconductor industry, driving continuous advancements in computing power and efficiency. But shrinking transistors isn't just about making things smaller. It requires breakthrough in materials, design, and manufacturing techniques. Today, we are operating at nanometer scale, an extraordinary level of miniaturization. For example, the latest Qualcomm Snapdragon 8 Gen 3 processor manufactured using 3 nanometer technology. This processor powers some of the most advanced smartphones today, packing billions of transistors into a chip smaller than a fingernail. And its rival, Apple's A16 Bionic chip, built using 4 nanometer technology, contains an astounding 16 billion transistors. To put this into perspective, the Apollo guidance computer, which guided humans to the moon, operated with just 20,000 transistors. While the Moore's law fueled decades of technological advancements, the shrinking size of transistor is nearing its physical limits. Now the world is turning to next big leap, quantum computing. Unlike classical computers, which operate on binary data, quantum computers use something called as qubits, which can represent 1, 0 or both simultaneously, a concept called superposition. This unlocks unparalleled computational power, which will change everything the way we look at computers. AI is also playing a pivotal role in this transformation, optimizing chip designs and aiding the development of quantum systems. While quantum computing remains in its infancy, scientists are racing to overcome challenges like stability and scalability. From room-sized relay machines to packing billions of transistors in our smartphones, and now the dawn of quantum computing, with AI leading the way into a new era of possibilities.